In part 2 of problem 1, we're told that we've made 100 die rolls, taken their average and called it A. Called the best Gaussian or normal approximation to A prime. So remember from part 1, we know that A is approximately normally distributed. So let's just say it is normally distributed and call it A prime. And now we're asked to find the bounds of an interval such that A prime is in that interval exactly 90% of the time. Well, in order to do this, let's first find out some pertinent information about A prime. Recall, as we saw in part 1, the expected value of A prime is going to be the expected value of a single die roll, which is 3.5, halfway between 1 and 6. And the standard deviation of A prime is going to be the standard deviation of a single die roll, which is square root of 35 over 12, or approximately 1.7, divided by the square root of the number of die rolls, which in our case is square root of 100, or 10. So that gives us a standard deviation of approximately 0.17. What do we do next? Well, we can consult a table to discover that a normal variable, any normal variable, falls between 1.64 standard deviations below and above its mean precisely 90% of the time. Well, approximately 1.64. So any normal variable falls between 1.64 standard deviations below and above its mean %90 of the time. So we should just take our interval to go from 1.64 standard deviations below the mean and 1.64 standard deviations above the mean. So we can take AB to be 3.5 minus 1.64 times 0.17 to 3.5 plus 1.64 times 0.17. Alright, makes sense? That's the interval we'll want to use if we want to center it on the mean. Of course, we don't have to center it on the mean, but that would be the most convenient. The one question remaining is, how did we discover that any normal variable falls between 1.64 standard deviations of its mean 90% of the time? How did we know how many standard deviations we'd have to go out to encompass 90% of the probability of a normal variable? Like I said, we can just discover this on a table or using a computer, but you may not have consulted such tables before. You might find it useful for me to go over how to use such a table. Well, such a table can be given to you in many different forms, but often such a table is given to you in a form where, rather than telling you directly the amount of probability within a certain number of standard deviations of the mean, often it tells you instead how much probability is at most a certain number of standard deviations above the mean. So what we want to find is, let me just draw a random variable here. I'm drawing a graph of the probability density function for a normal random variable. So suppose we wanted to find the point at which that many standard deviations out from the mean encompasses 90% of the probability. Well, by symmetry, that means that what's remaining is 5% of the probability above that many standard deviations above the mean, and 5% of the probability below that many standard deviations below the mean. So that overall, 90% of the probability is below z standard deviations above the mean if z standard deviations from the mean encompasses 90% of the probability. Why did I care to put it in this form? So that we've transformed the question from how many standard deviations away from the mean encompasses a certain probability to how many standard deviations above the mean is the upper bound on a interval that goes all the way to negative infinity and encompasses a certain amount of probability. That phrasing is odd, but why did I transform it in this way? Well, because let's look at a normal distribution table as it's often given. This table says if you give me a number of standard deviations above the mean, I'll tell you the probability of falling below that many standard deviations above the mean. So this table is not directly given to us in the form we'd want. You could find tables given to you in the form you'd want for this problem, but very often they're given to you in this form instead. So I've transformed the question to the appropriate version to use for this table. We wanted to know how many standard deviations away from the mean would encompass 90% of the probability. We discovered that whatever that value z is, it's the same as the value such that 95% of the probability is below z many standard deviations above the mean, or in other words, on a standard normal variable, 95% of the probability is below z. We want to find out what z makes that happen. If we look at this table, we'll see that such a z is somewhere in between 1.64 and 1.65. And so it's approximately 1.64. That's where the 1.64 came in our solution as demonstrated earlier. Of course, in the modern era, there's really no reason that you'd have to use tables. You can just go find apps. You could actually use a calculator that directly solved the problem for you in whatever format you wanted. You could find a calculator and say, tell me how many standard deviations away from the mean I'd have to go to encompass 90% of the probability, or whatever it was you were doing. But if you did happen to be stranded on an island with nothing but a mid-20th century standard normal distribution table given to you in terms of the cumulative distribution function, and you wanted to solve this problem, this is how you would do it.